Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about integration by partial fractions when we have repeated quadratic factors. In the last three videos we talked about how we worked with linear factors, repeated linear factors, and quadratic factors. This time we're going to talk about how we deal with integrating a function, a rational function that has repeated quadratic factors. So we're going to do this example. Notice that this factor in the denominator is linear. This is quadratic because it's degree 2, but it's repeated. So let's get started. Our first step is to take this fraction and divide it into its partial fractions. So the first fraction will have a denominator of x plus 1, which is linear. So our numerator is just a constant, which we'll call a. Our next denominator will be x squared plus 1, which is quadratic. So our numerator will be bx plus c. And our last fraction will be x squared plus 1 squared. And that is quadratic repeated. So our numerator will be dx plus e. And our goal is to find the values of a, b, c, d, and e. In order to do that, we're going to multiply both sides of the equation by the lowest common denominator. So I will end up with the left-hand side just being the numerator, because the whole denominator will cancel. This term, the x plus 1, cancels, but I'll be left with a times x squared plus 1 squared. When I multiply this fraction by my lowest common denominator, I will end up with x plus 1 and x squared plus 1, because one of the x squared plus 1 factors cancel. And the last fraction, the x squared plus 1 squared will cancel, and I'll be left with x plus 1. Our next step is now to multiply all of this out and get rid of all of these brackets to get individual terms. I don't really have room to show all of those terms, so I'm going to just jump ahead a couple of steps and group those terms according to the powers of x. So I'll have my x to the 4th term, my x cubed term, and so on. So here's what I end up with once I've expanded all of this and grouped all of my like terms together. I didn't have room all in one line, but hopefully you get the idea. So here's the coefficient for my x to the 4th term, my x cubed term, and so on. And what I want to do is make 5 different equations based on these coefficients. Notice there's an x to the 4th term here, but not here. So that means the coefficient of the x 4th term has to be a 0. So let's write out all of our equations. Number 1, a plus b has to equal 0, because the coefficients of the x 4th term have to be equivalent. Then this coefficient has to equal the coefficient here, which is negative 1. So b plus c has to equal negative 1. Then this has to equal this coefficient, which is 1. So 2a plus b plus c plus d has to equal 1. Equation 4 is b plus c plus d plus e has to equal the coefficient for x, which is 1. And the last equation is a plus c plus e has to equal coefficient of our constant, which is 3. In order to solve for these variables, I have 5 equations and 5 unknowns. I need to know at least what one of those variables equals to start with. And the way I'm going to do that is I'm going to let x equal negative 1, which will eliminate these terms and will allow me to solve for a. Once I have a, I can find b. Once I have b, I can find c, and so on. So I'm going to let x equal negative 1. So I'll have negative 1 cubed and a negative in front, plus negative 1 squared, plus negative 1, plus 3 equals a times negative 1 squared plus 1. And then when x is negative 1, that term is 0 and that term is 0. So that's going to be 1 plus 1 minus 1 plus 3 equals 2 squared, so 4a. 4 equals 4a, so a is equal to 1. Then when I put that value of a into the first equation, 1 plus b is equal to 0, I'll get b equals negative 1. Then when I put that value into the second equation, negative 1 plus c is equal to negative 1. Therefore, c is equal to 0. When I put those values in equation 3, I'll get 2 plus negative 1 plus 0 plus d is equal to 1. And that gives me a value of 0 for d. And to get e, I don't even need this fourth equation. I'll just go to the simplest one. I have 1 plus 0 plus e is equal to 3. So e has to equal 2. Now let's plug the rest of these values in for the other letters. And therefore this fraction can be split into these partial fractions. Now let's do the integration. So we've broken up this one fraction into these 3 partial fractions. Then I've made separate integrals. I've taken the negative sign outside of the integral sign, and I've taken the 2 outside just to make it a little bit simpler. Now let's look at each of these and see if we can integrate them. This fits our basic log pattern. We've seen this come up in previous examples. So this is 1 over u du. So the integral of this is the natural log of the absolute value of x plus 1. This term can be integrated using the same pattern, the basic log pattern. It's 1 over u, but u is x squared plus 1. Therefore, my du factor is 2x dx. I need a coefficient of 2, which I can introduce as long as I balance it with a 1/2. I can do that with coefficients. And now it fits my pattern, 1 over u du. So it'll be 1/2. The integral of 1 over u du is the natural log of the absolute value of u. In this case, because u is x squared plus 1, that can never be negative. I don't need the absolute value signs. In order to integrate this last term, I have to use another technique of integration. It doesn't fit any of our patterns. However, I can use trig substitution to integrate this, and I covered that in the topic before I did partial fractions. If you go back about 4 or 5 videos in the integration playlist, you will find integration by trig substitution. So that's the technique I'm going to use. I'm going to come back to this part of it. I want to just do that separately because I'm going to have to get into a different variable and then I'll come back. So let's just do this term. So the substitution I'm going to use, because it's x squared plus 1, which we can think of as a squared, where a is equal to 1. So the substitution I'm going to use is I'm going to let x equal a tan theta. Since a is equal to 1, x is equal to tan theta. So I'm going to replace x with tan theta, but I also have to replace dx. In order to find what dx is equal to, I'm going to take the derivative of both sides with respect to theta. The derivative of tan theta is secant squared theta. And then I'm just going to multiply both sides by d theta. So dx is equal to this, x is equal to that. I'm going to replace those, the x and the dx, with those values. Now, tan squared theta, I'm just going to simply write like this. I am going to replace this. I'm going to use one of my Pythagorean identities that says tan squared theta plus 1 is equal to secant squared theta. It's going back to some trig identities. So I'm going to replace that with secant squared theta. and that will be equal to secant squared theta over secant to the 4th power theta. Secant squared cancels in the numerator and the denominator, so I'll have 1 over secant squared theta. And we know that 1 over secant is cosine, so 1 over secant squared theta will be cosine squared theta. We could look at a table to integrate that, or what I'm going to do is I'm going to use my double angle identity to replace that. One of the double angle trig identities says that the cos of 2 theta is equal to 2 times cos squared theta minus 1. If we add a 1 to both sides, we know that 2 cos squared theta will equal to cos 2 theta plus 1. Let's move that 2 inside, and let's replace this with this expression. So this will be equal to the integral of cos of 2 theta plus 1. Now we'll break these two terms up. So we have the integral of cos 2 theta d theta plus the integral of 1 d theta. We've learned that the integral of cos of u du is equal to the sine of u. We're just missing a coefficient here of 2 to get our du factor. So I can introduce the coefficient as long as I balance it. So now I have cos of u du. The integral of that is simply sine of u, so sine of 2 theta. And the integral of 1 d theta is just theta. We'll worry about the constant of integration at the very end of our question. So we've been able to integrate this, but we've integrated in terms of theta, not x. Now we have to go back to x. So let's do that. Okay, remember we said that x was equal to tan theta. So let's take a look at our right triangle and use this information to find all of the sides. So x is simply x over 1. Tan of an angle is defined as the ratio of the opposite over the adjacent. So this would be x, this would be 1. And then using our right triangle theorem, x squared plus 1 squared, take the square root, and that gives us our hypotenuse. So x squared plus 1 to the 1/2 would be the hypotenuse. All right, let's go back to this. Now, we have 2 theta, not theta. So again, I'm going to use one of our double angle trig identities, which says that the sine of 2 times an angle will be 2 times the sine of theta, cos of theta. Now we can use this. One half times 2 is 1, so we've got sine theta, cos theta plus theta. Now let's write sine theta in terms of x. So we're going to write it as the ratio of the opposite side to the hypotenuse. So it would be x over x squared plus 1 to the 1/2. Cos theta is the adjacent side to the hypotenuse, so 1 over. And then how do we write theta? Well, if tan theta equals x, we can isolate theta by taking the inverse tan. So theta will be inverse tan of x. Let's simplify this to be x over x squared plus 1. So we've integrated that third term in our question to this. Now let's plug this back in to the rest of the equation. So now we found this integral to be x over x squared plus 1 plus the inverse tan of x. Now we're going to add our constant of integration. If you want to combine these log terms, go for it. I'm just going to leave it at this point here. Hopefully these last 4 videos help you in doing integration by partial fractions.